Hello and welcome to day 17 of my Advent of Code series for 2020. If you've missed any of the previous episodes and you want to check those out, click the playlist right up there and be sure to get subscribed to me and turn on notifications so you don't miss any of my future videos. So today we have day 17 called Conway cubes. And pretty much we need to figure out what's wrong with the energy source of our imaging satellite. And the way that it works is it has a pocket dimension which contains an infinite three-dimensional grid, and each of those contain a cube that is either in an active or inactive state. And the way that those cubes determine if they're in an inactive or active state is with a set of rules similar to like we had in one of the previous days with another sort of game of life adjacent thing. So here, if a cube is active and exactly 2 or 3 of its neighbors are also active, it remains active, otherwise it becomes inactive. And if it's inactive but exactly 3 of its neighbors are active, it becomes active, otherwise it remains inactive. So what we need to do for this first part is for that three-dimensional infinite space, we need to determine how many things are going to be on after 6 cycles. So it works through an example showing things by slice here. And we need to go ahead and find what it's going to be in the end. So I recommend you go ahead and give this a try yourself, and we'll jump into my solution right about now. Okay, so the first thing you might notice, I think this is the first time other than deep copy that I've imported something just because it made the code way easier to use product from itertools here. So what I'm going ahead and doing is we have our read init, which is just reading in each line of our input. Our input is just a slice of our grid right here. And then what I'm doing is I have this init on function. So what this is doing is this is saying at the start when it gets called, it's going to get called with an init, which is going to be our input, and a number of dimensions, which is going to be how many dimensions our space is, and it's going to return back to us a set of all of the locations that start as on. So the way that this works is it initializes a set, and it's essentially just looping through every location in our input. And what it is doing on each of those locations is if it has a pound sign, then it adds in a tuple of I and j, which is going to be the location in our input, and then it adds a bunch of zeros for the rest of the dimensions, which is just going to be however many dimensions we have in total. So for part 1, this is 3 dimensions, and we multiply in a bunch of zeros to our list there, and we just do that for -2 because we already have I and j settled. So that will give us a list, and then we convert it to a tuple just because these should all just be immutable locations in the set. It makes the set serialization faster if we do it like that. And then we finally just return that set at the end. So then we have our iter function. So what this does is this actually goes through and does our iteration on our init for however many dimensions, for however many number of steps. So what we do here is we first call that init on function that we saw before to get our initial grid, and then for however many steps we have, we're going to essentially just do this however many times. So what we're doing here is I'm initializing a dictionary, and then I am looping through all of the locations that are currently on, because if you'll remember, those are the ones that everything else happens based on. And then what I'm doing is I am looping through the neighbors. So how I'm doing this for the neighbors is, if you'll see here, I have -1 is 0 and 1, and I'm going to find the product of all of those with a repeat equal to dimensions. So this is going to give me, for however many dimensions we have, which in the first part is 3, it's going to give me every possible triple, since we have 3 dimensions, that is composed of -1, 0, and 1. So then what I'm doing here is new is going to be a tuple, which is just that it works with all of our other tuples, of mapping the sum function onto zip of location and neighbor. So that is pretty much just saying this is the actual location that we're checking, this is the actual neighbor. So this neighbor function, it just holds a sort of mapping of all of the relative locations to the location that we're currently checking, and then this new right here is going to be our actual location. And what we're doing is if new doesn't equal location, because if you'll remember, we are going to have the one case where this is going to be 0, 0, 0, or if we had more dimensions, then more zeros. So we just want to make sure that's not the case. And if that's not the case, then we check if it's in our keys of our C right here. And if it's not, then we go ahead and just initialize it with a 1. And if it is, then we just go ahead and add 1. So this is going to be how many active neighbors it has. Because if you remember, this loop is going to go through every single location that's currently on. So we're checking all of the locations next to it and seeing if those, and just saying how many neighbors each of those have. So then what we do here is sort of the meat of it, which is the actual checking for it. So stay on is going to give us a set of locations that we need to stay on. So what we're doing here is we're checking in our on grid. We are making sure that it has either 2 or 3 neighbors, and then there's also a case where it never gets hit by the neighbor thing. So, and I just have a little check here to avoid getting an error to make sure that it's in c.keys. This could be circumvented if you wanted to go ahead and use a a counter from collections. So that would simplify this code quite a bit here. What you could do is you could completely omit this block of code right here, and you could switch this to just saying c sub new plus equals 1. But I wanted to avoid using as many external libraries as I could. I just couldn't help myself on product here because it makes this so much cleaner. So that, and then we're checking to make sure it has either 2 or 3 neighbors. So if it was on previously, so if it's in our on set and it has either 2 or 3 neighbors that are on, then it stays on, so it goes into the stay on set. And then in our turn on set, we're going to loop through the locations in c.items. So c.items is going to give us a double of both the key and the value inside of C. So if it was not in on previously, so on, if you'll remember, is our set that contains all the things that were on in the previous iteration. So if it wasn't on before and it has exactly 3 neighbors, then it turns on. And then what we're doing here is we are just returning the union of these 2 sets. So what this is going to give us is this is going to give us all of the things that need to stay on, plus all of the things that need to turn on into our on thing here. And then if you'll remember, we loop through that for however many times our steps is. And then at the end, we just return the length of on, which is going to give us how many actual things are on. So with that done, we can jump into part 2, and we'll see that part 2 is just doing the same thing, but for 4 spatial dimensions. So if you'll, sorry about that. So it's still giving us that same 2D slice, but we just need to do it for 4 dimensions instead of 3 dimensions. So because of the way that we structured this using tuples instead of trying to actually build a data structure that mirrors our data, this is super easy. So if you didn't have a dimensions thing before and you were just using 3 here hard-coded, then you could just switch this to using a dimensions thing. So if you'll notice, for part 2, we just go ahead and bump the dimensions up to 4, and that is it. So that is it for part 2. We use the same exact code as for part 3, except for our tuples will be 1 dimension longer, which, because we're using product here with repeat, I initially wasn't using product here. I was just looping through all of these options, but then once we got the 4th dimension thing, I switched it to use this because repeat is just such a useful tool for that. And I didn't want to have 4 nested for loops. 3 already looked ridiculous there, which brought us to a total of 5 nested for loops there. But yeah, that is going to be it for today. So today is just another sort of game of life clone, which we've already seen this year, which is a little bit disappointing, but I guess it was slightly different, and I tried my best to take a slightly different approach so I could show you something that was different than what I had done in that previous day. So that is going to be it for me for today. If you enjoyed, be sure to leave a like on the video. Be sure to get subscribed so you don't miss any future videos, and I will see you in the next one. Goodbye.